let's write down this one. They're using, what's their resistivity of the wire? Now notice their units is 0.35 for their resistivity, 0.35 ohm centimeter, not ohm meter. Then their length is 6.33 centimeters. And then their area is 1.91 centimeters squared. And then their resistance is 1.16 ohms. So let's calculate it, and let's say this is we can call this the experimental resistance because it's the one that the simulation gave us, right? So then from our equation, we would say R is rho L over A, and then rho is going to be what? 0.35 ohm centimeter. Length is 6.33 centimeters. For 1.91 centimeters squared. Well, yeah, here you don't even have to do any change of from centimeter to meter. If everything is given to you in centimeter, you can just multiply this by this and or divide by that, and it's straight up calculated. 0.35 times 6.33 divided by 1.91. Yep, 1.16. 1.16 ohms. Yep, okay, so you see it works just from that simple simulation. Okay, how about if you have a resistor that is something like this? Let's say I'm going to use the same, let's say I'm going to use the same dimensions. So let's say the initial area was 1.91 centimeters squared. And then let's say it looks like a weird resistor like this. So let's say the area here was whatever we had in this example. And then let's say it's some kind of function that's increasing like a square function, right? So let's say by the time you get here, the area is, let's say 3.24 centimeters squared. And let's say the length from here to here is still, was it here, 6.33 centimeters. Okay, so now what would its resistance be? It would probably be, would it be smaller than this or bigger? If the opening is getting, if the area is getting bigger as you go, would it be smaller number than this or bigger number? How many would say smaller? I think resistance will be small. Okay, good. How many would say bigger? Anyone would say bigger? No? Okay. Seems like one person is voting smaller. Yeah, it should be smaller because the area does not stay 1.91. It increases, right? So what we need to do is come up with some kind of function for this. Maybe put the XY axis like this. XY axis, right? And then come up with some function that will tell us the height of this or the radius of it as a function of the length. So we could say, what's the initial radius? It's going to be, since the area is pi r squared, we can say the initial radius is, let's write it this way. Area initial is equal to pi r initial squared. So this is 1.91. So I can calculate what the initial radius of this is. Okay, so the initial radius is 0.7797255. That's still in centimeters, right? So centimeters. Okay, and then the final radius is going to be, so that's going to be the distance from here to here, our final. Then that's going to be a final over pi square root. So then I'll put here 3.24. 3.24 divided by pi square root 1.015544125. Yeah, so I see the radius is getting larger. So then how is the radius getting larger? We can have some kind of function. R f as a function of x is, let's say, alpha x squared plus r initial. Okay, so it's like growing like a square function. You see. So then I could say the r initial is your 0.77. And then the alpha would be some fudge factor that I need in order to describe how this square function is growing, such that by the time I get to 6.33 centimeters, my radius should be that. So then when I put here x is 6.33, times this number, then the final radius should be that. Okay, so then I'm going to take this number, minus 0.7797,255, right? And then divided by 6.33 squared. Alpha is going to be 0.005885256. So it's just some fudge factor that I need to make the square function fit that square behavior. or it could have been a linear behavior, whatever the problem tells you. Right. Okay, then I'm going to do an integral. I'm going to take a small piece of this wire. And then I'm going to say the resistance of that, right? Okay, let's go to a different page. The resistance of that dr is equal to rho dx over A. So it's a small piece of the wire, right? So it's the resistivity of the wire times the dx, which is this small incremental length of the wire, times the area of this wire, this cross-sectional area. So the current is flowing this way. So then I'm saying, if you take a piece of that wire, its resistance is its resistivity times its small little length over its area, right? And then that's going to be equal to its resistivity times dx over pi r squared. And then now integrate that. If the resistivity is constant throughout the length of the wire, for now I'm going to assume that, then I'll change that up also. If the resistivity is constant, then I can take it out of the integral. Then I could say dx over, and then the r is the function that we came up with, this function right here, alpha x squared plus r initial, where alpha was that. So I'm going to write that all down. You know what? Let me take a picture of this. This is a classic case where you're turning the page over. Okay. So then alpha is going to be 0.005885256 x squared plus 0.7797255. Okay, but then squared. So this is the radius. This is the radius of the, well, you know what? This R and this R is confusing because this is the resistance. I should perhaps do small r here for small, the radius. So let's do here small r, so you won't confuse with the resistance. Small r, small r, small r, small r. Okay. I think that's it. Okay, and then the resistivity was, in the problem, was given as 0.35, right? 0.35. And then you're integrating this from 0 to the length was what? 6.33. Right? Okay. Okay, now we go to one divided by 0.0 0.588 5256 x squared plus 0.7797 255 squared. Okay, let's last check 588 5256 0.7797 255 0.6.33. Okay, so the integral itself is giving me 8.75657 223787. And then multiply that by 0.35 over pi. Mm-hmm. 75657 223787. Oh, times 0.35 divided by pi. The resistance came out 0.9756 ohms. Is that right? What was the previous resistance we got? Yeah, 1.16, so slightly smaller, right? Yep, you got it. Because it opens up, the area is changing, it does come out larger. Now part B, actually this could be part C, because this could be part A of the problem, right? Where it was a uniform radius, then part B can be this. Okay, change up the radius. And then part C could be, let's say the temperature here is 20 Celsius. And let's say at this end, you hold the temperature of the wire at 80 Celsius. So now the resistivity is increasing linearly, right? Beyond this value. Let's see, what was the resistivity? 0.35, right? So the resistivity is increasing. So let's say the coefficient is what? The alpha would have. Oh, don't confuse it with this alpha, but this is the coefficient, what was it? The temperature coefficient. So let's give it some temperature coefficient. Let's say it's increasing by, let's use one of the previous temperature coefficients. Okay, let's say something like, okay, let's say it's copper, something like that. Okay, so let's say it's 4.5 times 10 to the minus 3. So let's say that's the temperature coefficient. So then what happens is the resistivity of the material now is increasing as you go this way. If you're holding this side of the wire at 80 and this side of the wire at 20, right? It's the wire is getting warmer as you go that way, linearly. So then what would be the temperature? What would be the temperature of the wire? So we would have to kind of come up. So if this side is being held at 20 Celsius. And this side is being held at 80. What would be the temperature of the wire as a function of the x? So that would be a linear function, right? Let's say the temperature is increasing linearly. So mx plus b. B would be the initial temperature, which is 20. And then what would the slope be? M would be the difference in the temperature, 80 minus 20, over the length, 6.33 x. So that's kind of just basic rise over run. So the temperature is increasing by 60 Celsius. So you have 60 over 6.33 x plus 20. So when the x is 0, then the initial temperature is 20. And then when the x is 80, and you do this, when the x is 6.33, right? The 6.333 is going to cancel with this, and then you're just going to get 80. Yeah, okay, that makes sense. So this is the temperature as a function of the x. Then the resistance of the resistivity of the wire is going to be equal to rho 0, 1 plus alpha T minus 20. And then the resistivity of the wire was what? 0.35, right? So then that'd be 0.35, 1 plus, and then we said alpha is 4.5 times 10 to the minus 3. And then you put this T function in there. You say 60 over 6.33 x plus 20 minus 20. So that's telling you what the resistivity is doing as a function of x. And the 20 is canceling. And then let's see if this makes sense. So when x is equal to 0, right, then this disappears. When the x is 0, this whole thing disappears. And then your resistivity is 0.35 here. So that's the initial resistivity, 0.35. Then when x is equal to 6.33, then you're going to multiply 60 by that, add 1 to it, and that will give you the final resistivity here. Yeah, so that makes sense. The equation works. Okay, so then you put this function where? Into the resistivity here. So instead of taking the resistivity out, you put it into this function, 0.35. Then you have here 1 plus 0.0045 times 60 over 6.33x. I guess you could still take the 0.35 out. Yeah, let's just take the 0.35 out. But this part you can't take out. 1 plus this part here. 1 plus 0.0045, right? The 60 over 6.33x. That part it's got to stay. Okay, let's see here. 0.35. I always want to double check. Let's see here. Did this thing 0.35? This one 6.x. Okay. Now the resistance might even be bigger than even before, even though it's opening up. But since the resistivity is increasing, so we go over here. So on the top, you're going to have 1 plus 0.0045 times 60x divided by 6.33. Okay, so that makes sense. 1 plus 0.0045 60 6.33x. Okay. Yep. Okay, now let's go. Okay, it came out bigger. Yeah, before it was 8.7. Yep, and now it's 9.8357629. Yep, see, it all makes sense. So 9.8357629 times the 0.35 divided by pi. Ooh, it's still less than when it was uniform wire. R is 1.0958 ohms. Because it's opening up, that's really affecting it. Yeah, so it's still less, but it definitely is bigger than when the temperature is the same. 1.0958 ohms. Cool, we laid the good groundwork. So we've covered how to do resistance of wires, variable wires, resistivity. We even talked about the gauge.